Okay, so before we hop in, I have some stuff to tell you guys. Hi, I'm Shweta from AstronEra and welcome you all for AstroStream. This is our fourth episode with Ellen today. And this week we actually organized a little quiz and we have the results. Lots of you all gave correct answers, and we have a few winners who we are going to announce now. After this announcement and after the session with Ellen, we are going to have an announcement at the end of this session. Actually, two announcements at the end of the whole session. So stay tuned for to know what these announcements are. And now I'm again taking this over to Ellen, and she can tell who all won the quiz. Okay, Ellen. We are announcing the names of the winners of the quiz right now, and I have two more exciting announcements which will be at the end of this episode. Yes, so congratulations, you guys. You guys have given the correct answers in the quiz about black hole, the quiz with Ellen. So, Ellen, we can start with our session now.
Sort of like how we indirectly find methods for detecting exoplanets, as we talked about last week, since they're so tiny. You'll find this theme a lot in astronomy. A lot of objects are challenging or impossible to find. And with black holes, we can't directly image these. And so astronomers find surrounding objects to look at instead and see how they move and how they're affected by what we're actually trying to target to learn more information about them. So before I kind of talk about black holes, so this image on the right, or this little time lapse, I hope that's playing. I think it's playing on my end, so it should be good. But this is actually a time lapse over 10 years. You might be able to see the number in the corner from 1997 to 2017. And this was data put together by the Keck UCLA Galactic Center Group. And this is actually data from our own Milky Way galaxy. This is us pointing telescopes and collecting observations from our galactic center towards a region called Sagittarius A. And it's thought that there might be a supermassive black hole at the center of our galaxy, as well as every other galaxy. There's thought to be a black hole, and in some cases a supermassive black hole. But hopefully you can see, it's kind of a small graphic, but all these stellar orbits seem to have something that they're orbiting around. There's some gravitational effect on all these dots or all these stars or large masses of stars here. So I thought that was a really cool graphic to demonstrate how previously, and even without taking images directly of black holes and of galaxies, we have these other pieces of evidence that black holes exist. And this is how we think, there must be something that is gravitationally pulling all these stars at the center of galaxies. And it's pretty cool that this is our own galaxy as well. Okay, so before I get into the research that my team did of gathering data on galaxies that were thought to have black holes in them, I wanted to touch on the large event that happened in April of 2019, where the Event Horizon Telescope Collaboration announced the first image of a black hole ever. And you probably heard of it. It was a huge announcement. The photo looked something like this. And I kind of wanted to just briefly touch on a little bit on how they got that image so that you can see the different methods on how we are collecting data on black holes. The method that my team and I used to image galaxies was definitely a lot different, and the final goal was a lot different as well in what data we were trying to collect. So I thought it was just an interesting thing to go over. But basically, there's something called the Event Horizon Telescope. And I think that this telescope has been around for a few years, although in 2017, there was a certain list of telescopes or observatories around the world that were part of this collaboration, and it changes a little bit each year. And I think in 2021, there's going to be new observatories that are added on to this collaboration. So what it is all around the world, different specifically radio observatories, sign up to be part of this collaboration and be part of the Event Horizon Telescope, where you can create an effective diameter spanning the distance between these observatories. So instead of having one observatory that you're trying to build the aperture to be 10 meters, specifically for radio astronomy, you can't do this with optical astronomy. And I don't know enough about radio astronomy to go way too in depth, but you can have an observatory at the South Pole, an observatory in the US, observatory in South America, like is shown on this map. And by combining data from all sets and all locations, create the effect that you're actually gathering data over a much larger aperture, which is really fantastic. And that's kind of why it took so many years for this image to be produced, is because you really needed an aperture so large and so different than what we've done before. And this background image is one of the, I think maybe like 10 or 12 different observatories that are part of this effort, called the sub-millimeter array, which is an 8-element, so it has 8 telescopes in and of itself, near the summit of Mauna Kea in Hawaii. And then just a bit on how they captured this image. So again, they are doing radio astronomy. Everything that I've done has been optical astronomy, optical imaging for scientific applications, and I'll get more into what my team did. But they collected radio signals from each of these telescopes. So each of the lists that I put here represents a line of data coming from a different observatory, and the radio signal will get digitally converted. And then an atomic clock was used to mark the exact time. And this data was transported on hard drives all to the same location on Earth. And then a lot of data reduction was done to produce this image. And I believe it was the difference in time, and that's why the atomic clocks were so important, the micro difference in times of when these radio signals were hitting each of these observatories and each of these radio telescopes around the world. And that's what kind of gave them a lot of the data necessary to produce this image. And I also should have mentioned in the beginning, so it's called the Event Horizon Telescope because in a black hole, where you start to see this ring of light around, that is called the event horizon of a black hole. And that's kind of where things start to escape the speed of light and are higher velocity than the speed of light. And that's why you start to see some light around. All right. So intro to what my team did. We focused on imaging objects called active galactic nuclei, or AGNs. And these objects are extremely hot and extremely dense, and they reside at centers of extremely luminous galaxies. We don't exactly know why these galaxies are so much more luminous than every other one. There's a lot of data over time still being taken, and what we did was an effort over, I think, 3 years. I was part of this research for a couple of years, but it was very slow observations and slow change, looking for small changes in time of these different galaxies and wondering if the changes we were seeing were more based on, are we actually seeing different types of galaxies, or are we just seeing the same type of galaxy from a different viewpoint? Because from Earth, we're stuck with one viewpoint of an object. Are we just seeing the side of it? Or are we seeing the back of it? So that was something that that was a really interesting thing that we delved into as well. But anyways, and there are two types of galaxies, and the plot on the left shows the difference between an active galaxy and a normal galaxy. So in the electromagnetic spectrum, from radio, infrared, visible to X-ray, a normal galaxy will have an intensity curve, or a spectral intensity curve, of the purple line below. So you can see that it peaks in the infrared and visible, and you don't really get a lot of radio and X-ray intensity signal from it. Whereas the active galaxy line, the blue line above, you are getting intense spectral response all the way across radio, infrared, visible, and X-ray. So that is a good indicator that we can observe these active galaxies with radio telescopes, with infrared telescopes, visible telescopes, and X-ray telescopes, which is pretty cool. And for what is an active galaxy again? An active galaxy is a galaxy that has this active galactic nuclei, or this like very, very extremely luminous center that is not thought to be produced from just stars. It's thought to be produced from some other thing that's going on in the center, and this is theorized to be a black hole. And that these supermassive black holes are pulling so much light and have such a strong gravitational effect. You can kind of see in the graphic on the right that it starts to create an accretion disk of all this really dense and luminous and bright matter around it. And these are the kind of objects that we were trying to observe and trying to understand. A bit about our team and what equipment we used. We were called the SAMP team, which stood for the Seoul AGN Monitoring Project. This was a collaboration between our small team at Cal Poly and I believe a team at UCLA, as well as a larger team over in South Korea. And we were a dedicated team for years to observe these active galactic nuclei and specifically try to extract black hole masses by observing these bright, bright galaxies. And we did our observations at Lick Observatory. This was so fun, a lot different of an experience than working at the small observatory on campus. So Lick Observatory is about a 3-hour drive from where I went to school. And then the next thought would be, okay, like you've got to drive to this telescope 3 hours away every week to do observations. But we actually had a remote setup so we could control the telescope from a lab on campus and do everything we needed to do full nights of observations. You can see a picture of me and my team on the left, and that's us under the big telescope that we got to use for this project. The aperture diameter was a whole meter, which is about 40 inches, and especially for optical telescopes, that is a ridiculous aperture diameter, and at that point you're seeing such dim objects that you could never see with your eyes, and you can see so far into space and get images of galaxies, nebula, and like it was so fun. And yeah, focal length of 17 meters and a ratio of f17, which means we are looking at very narrow fields of view in space, and we're looking very deep into space, and that's really useful for these objects that we're looking at. And then we used a CCD camera on it. Those are just some specs that I found online of the telescope or the setup at this telescope. And this was called the nickel 1 meter telescope, which is pictured on the right. And another fun part about this was that we got to one time go up to this observatory on Mount Hamilton. Mount Hamilton is like 5,000 feet up, and it was beautiful. We got to be there for a weekend and get officially checked out as astronomy observers because we had to be trained by the professional astronomers there before we could go ahead and use the equipment remotely. And a little bit about going through a night of observing active galactic nuclei, or AGNs. And a lot of this is a little bit similar to what I talked about for observing exoplanet transits last week. So if you want to get a little bit more information on the pointing or the focusing, then that works as well. Sorry. Getting notifications popping up. Okay. So the first thing obviously was to plan. We had to plan an AGN target list. And thankfully, another team did this part for us. So we didn't have to go search for galaxies that would be up at night. The team over in South Korea would send us an observing list every week or so. And this was important because we would try to observe about 20 galaxies every single night that we were doing this effort. And the sky changes very rapidly, and this is where hour angle is really important in astronomy objects. The hour angle of an object, when you're observing it, you want to be as close to zero as possible. And the hour angle is going to change over time. So once an object rises above the horizon for your local time, it's going to have an hour angle of about, I forgot if it's positive or negative, but the magnitude's about 4 or 5. And as it rises and gets closer to zenith, or like right above you, then it's going to reach hour angle 0. And that would be like prime observing time. You want to be observing it when its hour angle is 0 so that you're getting the best data. And that's because of something called air mass. As an object is closer to the horizon, the air density is a lot higher, and that's why objects are a lot dimmer, and you usually don't see very bright stars right near the horizon because it's actually, or there is physically a higher air mass there. So we would get information about hour angle, and we would have a very specific timeline of, okay, you only have, an hour to do this object, because then you have to move on to your next object and your next object to make sure you can fit them all in one night and that they're all rising and setting at the right times. So it definitely takes a lot of planning. And then the other two pieces of information that you're probably more familiar with, right ascension and declination, which is just the astronomical coordinates that we needed to point at these objects, as well as the exposure time. And this was important because some galaxies were a lot brighter objects than others, so we would just be handed the correct exposure time to properly expose these galaxies and get good science data. And then the next step was very similar to what we did for exoplanet transits. We would take calibration images, and these were extremely important for getting good data later on. So the first type of calibration image we took every night was a bias frame. We would take several of these and combine them to create a master bias frame, and this removes inherent sensor and detector noise. This is a 0-second exposure, and these are subtracted from science images or the final galaxy images. And then the second type was a flat field frame. This is an actual exposure, so it's using the fact that it's got a lens or a telescope on it, so it removes the optical imperfections introduced by the lens or telescope. And these were taken of a flat uniform part of the sky, and these flat fields were divided from the science images. So once you subtract your bias frame from your science data and you divide your flat field frame from your science data, you'll have a much cleaner, visibly cleaner, you can see the difference, and you're getting more light data out of it. Data reduction. So what did we do with all these images? So for a specific galaxy, we're trying to find the mass of the black hole. And this equation in the bottom left roughly described what our team was doing. There was another guy on our team that was doing most of the data processing for this project, and so I can sort of briefly explain, but the image at the top left is one of the images from our previous data. And as you can see, it just looks like a normal star field. No obvious black hole there, but we would have to match these images up to star charts online and make sure that we were looking at the right field of the sky that we were supposed to. So for every object that was handed to us, we would have a link to the correct star chart, match it up like a puzzle, and then say, okay, yep, we're good. We're going to take a 300-second exposure of this galaxy, and then we're going to switch filters and take another 300-second exposure of this galaxy, and then we'll move on to our next object. So that's kind of how our night went, and it was always really fast-paced, and it was a good time and gave me a lot of good experience. But anyways, so we would take these images, and instead of, to compare and contrast the exoplanet transits, we would have 300 images of one object and put them together to see change over time, whereas we might only have a couple images of a galaxy with a black hole in one night. And what was interesting, or what was really used, was the change in these images over longer periods of time. So imaging a galaxy that was thought to have a black hole in March, and then imaging again in May, and then imaging again in July. And that's why this effort was so long, because you need that difference in time to be able to really see any difference. And what were we trying to extract out of these images? So again, we were doing photometry. We were extracting brightness over time. And this image to the right shows a spectrum, and what we were using for the phenomenon that allowed us to do this research was Doppler broadening, or broadening in the broadline region, which is something that would show a lot of fluctuations in these types of objects, in these active galactic nuclei, when there was changes in the accretion disk and how much matter was rapidly spinning and changing around these very dense gravitationally pulling objects. So we would measure the Doppler, or measure the broadline region, the velocity of this, as well as the radius of the broadline region, and using Kepler's laws, then we would be able to extract the mass of the black hole. And this is important because as we take images of and collect data and get masses from these different objects, then that feeds into how much we know about active galactic nuclei. How are they different from each other? Are there actually different types? Are there not actually different types? And how are they different from regular non-active galaxies as well? So that effort, I think, might even still be going. I know there are a couple other teams around the world who are investigating similar things. It's really a newer field in the past couple decades.
Are you there?
Yeah.
Yeah, I'm sorry, I had a little bit of power cut over here. We are starting the stream again, so you might just have to start a little bit from, just like 2-3 lines ago, and we'll be good to go.
Okay. Was I still on the same slide?
Yeah, you were on the same slide. It happened just like
Perfect.
1 minute ago. We can start now. You can start.
Perfect. Okay. So I think we might have cut out there for a second. I'm not sure what was missed here, but basically taking, I guess, here. Sorry. All right. So being able to extract the velocity and the radius of these broadline regions from the active galactic nuclei, we were able to extract the masses of the black holes, and collecting this mass data was really important for being able to show differences in the predicted masses and predicted luminosities of these objects compared to what we thought, and just add to our existing knowledge, being able to, and especially adding to the effort of seeing what different types of AGNs exist. If there are different types, some people divide it into type 1 and type 2, although other people think that it's just us looking at these galaxies from different rotations, and the fact that we are limited by one viewpoint on Earth in looking at these galaxies. So I'm really excited to see how these theories change over time. It's still definitely a very new topic, and this effort is still going on, I think, for our team. And there are a couple other teams in the world that are trying to do a similar thing in just specifically observing AGNs compared to normal galaxies. And I'm excited to see where the research goes. So I'll pass it back over to you.
Okay, perfect. Just a second. All right. That was very insightful session, and we have so many questions now. But before I jump into the questions that our viewers have asked, I have a question for you. I would like you to explain a little bit about the gravitational waves that we have received from the collision of two black holes. And maybe you can tell a little bit about the LIGO observatories as well, since it's very much related to the the black holes. Also, can you maybe put your own screen on full screen mode?
Oh, yeah.
Yeah.
Am I still sharing my screen? Can
Yes.
I stop sharing? Okay.
Yeah, you are sharing your screen. Okay, perfect. That's good.
Perfect.
Yeah.
Okay. I definitely want to talk to you about this topic more, because did you say the collision of, like, when two galaxies collide, sort of what would happen there?
Mm-hmm. Yeah, so basically,
Gotcha.
what
Okay.
did we receive with the results of LIGO, and how we observed that the two black holes were colliding with each other.
And did you say this was from something called LIGO?
Yeah, LIGO Observatory.
Okay, so and that observatory, so Lick Observatory, what we use to observe these AGNs, we never sadly got to observe sort of any events where two galaxies were colliding together.
Mm-hmm.
And I've never done research on that specific type of event. And I think, oh man, I think from what I've read before, if sometimes when two galaxies collide, they can combine into one galaxy.
Mm-hmm.
I don't know. I'm trying to think of like the sort of gravitational effects of you have two very extremely luminous, extremely gravitationally pulling centers.
Yeah, yeah.
And what I would imagine is that one galaxy would probably start to orbit the other.
Mm-hmm.
Kind of like how binary star systems work of like one, or they might be close enough in gravitational pull where
Mm-hmm.
they're doing this dance of what they're trying to orbit each other, but they're both like fighting over it. So
Mm-hmm.
you kind of get the effect of a weird orbit for both of them. And I
Yeah.
would imagine it's the same for galaxies where one either starts completely orbiting the other. But then again, from our viewpoint, these objects are so far away that
Mm-hmm.
it's extremely difficult to observe these things too. So then when observing them, it's like, okay, why is this singular point just becoming more bright and
Yeah.
like dimming again and becoming more bright? It's like, it might be two galaxies happening, but we have no
Mm-hmm.
idea.
Yeah,
So
yeah.
I think it's definitely where a lot of the uncertainty comes from.
Yeah.
But yeah, not a topic that I know enough about.
Mm-hmm. Yeah, actually, I was also talking about this observatory LIGO. In India, also, it is building up now. So, I think 2 years ago or 3 years ago, or back in 2017, we discovered that two black holes kind of merged onto each other, and we experienced gravitational waves on the Earth. Like, Earth sort of wobbled a little bit. And the LIGO observatory, the way it is built, we can capture the gravitational waves uh, which were produced by two black holes merging with each other. So, such two massive entities with so much of gravity.
That's so interesting.
Yeah, right. Okay, so I'll move on to the.
Wow. I
Yeah.
actually, yeah.
Mhm. Okay, it's fine. So, let's
I'll
just
have
move
to
on to the
more about it later.
questions. Okay, let's move on to the questions now. So Amod Deshpande has a lot of questions to ask us, and he has practically spammed our inbox. So we will just start with his questions and then we'll move on. So he's asking, can you tell us some things in brief about the Event Horizon Telescope? I think he's talking about the event horizon of the black hole, like what you can explain more about the event horizon of the black hole.
Gotcha. Yeah. And I heard he also kind of briefly mentioned the telescope, so
Mm-hmm.
I'll mention it a bit again. So the event horizon, or I guess first of all, event horizon of a black hole is the region just outside of where it's, I guess, visibly black, where you can't see any light coming out of it. These objects are just so gravitationally pulling and dense that not even light can escape. So the actual black hole, obviously, you can't see any light coming out of it, but you do see light around it. And where
Mm-hmm.
you start to see light being able to escape, where you start to see anything that is faster than the speed of light, like kind of going out of it, that is the matter that has not, I guess, been pulled into it yet. But it is or as such a large, there's a lot of friction going on, and a lot of the matter sort of orbiting this like very dense center is
Mm-hmm.
extremely luminous, extremely energized. And that is called the accretion disk. And so just outside of that non-visible area is the event horizon of a black hole.
Mm-hmm.
And I guess a lot of things are going on, and it's a large event, so maybe that's
Yeah.
why they call it the event horizon. But the Event Horizon Telescope, or the EHT, is comprised of, I'm probably wrong, but 10 to 15 observatories around the
Mm-hmm.
world, and these are radio observatories that are collecting radio signals from um, from black holes and from the centers of galaxies. And the reason why it's called one telescope is it's combining the data from all these different observatories and creating an effective diameter for aperture of, the diameter of the Earth, which is insane compared to previously when we were just using diameters limited by one location on the Earth.
Yeah, okay, got it. So Amod is also asking, can we capture the radio jets of a black hole?
I believe yes. I think that's what at least part of what we're collecting with radio telescopes. And kind of there was one plot that I showed that kind of shows the difference between active galaxies and non-active galaxies. And the cool thing about active galaxies is that they show intensity in the radio part of the spectrum, as well as visible infrared and X-ray. Whereas if you were collecting radio signals of a regular galaxy or a non-active galaxy, then you would not get such strong intensity response of these radio jets or of any X-rays.
Okay. Also, his third question I would take, and this is going to be his last question, then we'll move on to the questions by others. So Amod is also asking, how big of a telescope aperture we need to observe a supermassive black hole?
It's a good question. I wish I could just set up my little telescope. It's like 10-inch diameter and start observing these things, which I probably could attempt. So galaxies are tricky because it's nothing that we are visibly seeing. And the larger aperture diameter you have, the more data you're going to get out of these very, very dim objects. And especially since they're oftentimes a lot dimmer than the other objects I was talking about in previous weeks, we do need larger telescopes. Although, for instance, my 10-inch telescope, I can do basic tracking on it, and I could point it at a galaxy that is like fairly dim. But even with a 10-inch or 8-inch telescope, you can see dim objects that have an apparent magnitude up to 12 or 14, which is like way past where our eyes can see. And if you were to take images of these galaxies once every month or so, you could probably do some of the same processes and see the effects of these supermassive black holes. Probably not take an image. I think the image specifically that came out of the 2019 collaboration, that was tied to the fact that it was using radio telescopes across the world, so that you really need some large aperture diameter, but totally possible to do sort of these indirect observations that we were doing.
Yeah. So actually the image that we took of the black hole in 2019, it wasn't obviously like a telescope kind of pointed towards the black hole and then captured the image, right? There was lots of computerized imaging and computerized rendering was involved. So can you maybe explain to me a little bit about that?
Yeah, and I wish I knew more. I've read a lot about this and been very interested in it since it came out, and honestly, some of it is a little bit over my head. But from what I understand, different areas in the world, and the fact that some of these observatories had then another set of observatories in and of itself meant we were getting a lot of small micro differences in radio signals, and all these radio signals were digitally converted into like analog signals, and then these signals were all combined together in a way to produce that image. But apart from that, I would have to do some more research and probably get some more expert advice.
Yeah, sure. Okay. So moving on to the question from Blesson Biju. Since we have discovered the existence of stellar mass binary black holes and have detected their gravitational waves, what kind of opportunities have opened up in this field? So
can you repeat the last part of that?
So what kind of opportunities have opened up in this field? Like what kind of researches we can still do about the black holes and after these discoveries were made?
Gotcha. As far as, I guess, like what kind of opportunities are available and like because these discoveries have already been made, I would say that I feel like it's almost the opposite of I feel like we've only started to kind of understand the difference between a lot of these types of galaxies, and there's like I feel like we've made it to like the 10% mark, and we have.
I think my software is again having some issue. All right, I don't know what issue we are facing today. Maybe since I
that is taking away optical imperfections, and I think a lot of that is from the atmosphere and combining the removal of bias frames and flat field frames from your final science images. That's going to get rid of a lot of the noise that you might see from atmospheric effects. Another and probably more pertinent thing that we do to combat atmospheric effects is resetting our focus every night. So the focus of the prime focus of your telescope is what's going to change based on atmospheric effects day to day. So we want to make sure to refocus our telescope because there might be a slightly different focus point night to night. And that'll help us combat atmospheric effects the most, I think.
Okay, all right. So Arnav Desai has asked, is it true that there are thousands of stellar black holes but only one supermassive black hole in our galaxy?
Good question. I want to say yes. There is thought to be only one supermassive black hole at the center of our galaxy. And I believe the general thought is one black hole or one supermassive black hole at the center of every galaxy. But that brings up another good point of like, are there ever two black holes, or is there ever the possibility of creation of a couple of them at the center of a galaxy? Or is that just not possible because one would have a larger mass than the other eventually and sort of eat it up? So, but yes, you're right. There are like thousands of them, but that's just because there are thousands of galaxies, and every one is theorized to have a black hole at the center.
Yeah, so actually, I mean, imagine this, that the black holes are created from the stars, right? It's what happens to a star when it's dying, or it's already dead, and then there is just lots of gravity in just one small spot. So it's a little bit hard for us to imagine that even the stars have life cycle, but yes, actually, to give you a quick view in a nutshell, the stars are born in a nebula, and depending on their sizes, they live their life. So the stars which are very massive, they live shorter life, and the stars which are kind of smaller, they live for a bit long time. But the larger stars have more probability to end up as black holes. So the sun, it won't become a black hole, but if there is a star which has mass of like 30 times more than the sun, it has a probability to become a black hole. So yeah, the sun is not going to be a black hole if that's what you're thinking about. Also, I mean, imagine there is a black hole in the center of the galaxy that we know of, but there are so many stars just in our own galaxy, like 40 million stars, and some of them are bigger than the sun, which might end up as black holes. So maybe in the future we might have more black holes in our own galaxy, and of course we know that there are black holes in the center of the other galaxies as well. Okay, now moving on to another question. Sanika J has asked, does the black hole have layers? If yes, how many layers does it have?
Layers. The black hole itself, I don't know about. There's, kind of the one light can't escape. This is the small, like can be, the size of your hand, very dense aftermath of a stellar death. Although, let me bring up to reference this diagram.
Yeah, so until Ellen brings up the diagram, I'd like to answer the question of Ardra Kishore, who has asked why sun cannot end up as a black hole. That is because the sun has kind of lower mass than we would expect from the stars who will end up as black holes. And actually all the stars have different kind of endings. So mostly the stars end up being a supernova, so they just eject lots of gas and dust in their surrounding space, and that's what we call as supernova. And this supernova has a remnant of the star in the center of it, which we call as pulsar in the beginning. When it's new, when the supernova is new, we call it a pulsar, or a neutron star. And then as it ends up its complete energy, it becomes a white dwarf. So sun is gonna die its death as white dwarf most probably, and it's gonna be a peaceful death. So that's why the sun won't become a black hole. Okay, yeah, so Ellen has the diagram now. She can continue explaining.
Yeah, so I guess this is what I would think of the different layers of these objects. This is specifically for active galactic nuclei. So again, active galaxy versus normal galaxy that has this very bright luminous center that we are observing these objects because the luminosity is not coming from just stars. It's coming from something else going on, and that something else is theorized to be black holes.
Mm-hmm.
So I like this diagram a lot. It kind of shows the very, very tiny black hole in the center, surrounded by the accretion disk as it's accreting different matter. And then it shows the jets and sort of just like all the matter that is highly energized and highly luminous. There's the broadline region that we use to determine the mass of the black hole, as well as the narrow line region, and surrounded by the obscuring torus. But yeah, there's all these kind of, I guess, like types of matter around and stuff that's ejected out because of the way that the black hole is gravitationally pulling this matter so densely. But I should look up and make sure that the black hole itself doesn't have different parts or layers to it, because maybe that's something that is being theorized as well, and that'd be pretty cool.
Mm-hmm. Okay, awesome. So Ashwini Dhumar has question. So she is asking, what kind of radiation is Hawking radiation? So can you tell a little bit more about what Hawking's radiation is?
I probably should know because it sounds like something that I should know, but I don't know what Hawking radiation is. So that is homework for myself.
Yeah, so actually it is released, that radiation is actually released from a black hole due to its quantum effect. Probably, I'm sorry, even I don't know much about it, but yeah, it is the radiation that is specifically emitted by black hole. And yeah, it's because of it has something to do with its quantum energy. So we have another question from just a second. We are getting spammed with so many questions now. I lost the question that we had before.
If
Okay.
there's any questions that I can in the future, like if anyone wants to reach me over Instagram, over LinkedIn, ask me questions, please.
Yeah.
I am totally available to talk, chat with
Yeah, yeah, yeah.
anyone. I
Okay,
probably
we'll
won't be able to
we'll
answer
just
them all
take
now.
like 2-3 more questions and then we will end up with the announcement. So we have question from Charu Agarwal. It is believed that black hole engulfs all the things around it. Of course, even light cannot get past through it. So why is that? And can you tell us how, if anybody survives in the black hole, or what happens to a person if that person goes near the black hole?
The question we all want to know: what happens when you fall into a black hole? Um, so, yeah, to answer the first part, as we already mentioned, black holes are created from stellar deaths, and this is important because stars are so large, right? The sun is many times more masses than the Earth. So as the star runs out of nuclear energy and of fuel over time, it eventually will become really unstable. The core becomes unstable and it collapses in on itself in like a supernova event. And because of these like high original mass of it, you can think of like how much mass is combined in just our own sun, and our own sun isn't even classified as a large star really. Um, so when the stars collapse, the ending object is usually, it can be the size of a house or a town, maybe at max, like, or just your hand. Like, it's all the masses combined into such a small area. Um, I think we don't really have a good, because we've never seen an event like this, so it's hard to kind of wrap our heads around. But when all that mass is combined into that small of a space, the gravitational pull is nothing like we like can ever imagine, and that's why light can't even escape.
Yeah, so like what happens to you if you go near the black hole is that you cannot even uh, pass from the event horizon, right? Like whatever they showed you on Interstellar was not really true. So actually when you come near to the event horizon, from that point, I'll give you example of this rubber band over here. So if this rubber band is near the event horizon, if the black hole is just under it and it's approaching the black hole, then it's just going to get stretched in so much. So if a human being goes near a black hole, the person is going to be stretched so much from DNA to DNA. So it's not possible for anybody to be alive if they are ever trying to go inside of the black hole. So as Ellen Ellen, just a moment again. Something happened. Just give me a second. Uh, yes. I hope we are back on. All right. I don't know what's going so wrong today. Okay. Yeah. All right. Okay. So yeah, I was just explaining that we will get stretched up so much if we even try to go near the black hole near its event horizon. Yes, so I think that's all about the questions today. I think if we take more, it's the connection is still going to make some issues. So before that happened, actually in the beginning, Ellen, your voice was a little bit low. So if you can you again please announce the names of the winners, and then we'll proceed to um, the other two exciting announcements that we have.
Yeah, the three winners were Raman Singh, Bhumika Taneja, and Pranjal Chaturvedi.
Yeah.
So congrats to you guys.
Yes,
You
so
probably
we
answered more
had
questions
we had
than me.
organized this little quizzer for all of you guys, a quiz with Ellen, and we were posting questions about black holes. And those who answered the questions correctly are the winners. So we have the three winners now: Raman Singh, Bhumisha Taneja, and Pranjal Chaturvedi. So congrats to both of you from Ellen and from all the team of AstronEra. We are going to be with Ellen in the next session, which is going to be on 21st of August, which is going to be our fourth session out of the 5 sessions that we are going to be with Ellen. And it is going to be about mining the moon, and we are going to do spectroscopy with that. So even I am excited about what she has for that with us to do. And yeah, so if you have any questions about imaging the moon and how to do spectroscopy, do send us those questions. We'll make sure that Ellen gets them, and in the next session, she'll surely try to cover all those in her talk. So I have two announcements now for you. One is that tomorrow we have Independence Day in India, so it is going to be our 73rd Independence Day, and that's why we are giving 73% discount on all of our courses on the AstronEra's website. The code is AstroIndia2020, all in capital. So you can get 73% discount on all the courses on astronera.org. So do make use of this opportunity and celebrate the Independence Day with us. Also, there is a big news for you since you all are enjoying such sessions with Ellen. We are bringing you more sessions, and they are going to be about astrobiology. So my friend from Israel, Reut, is going to take these sessions, and she is going to come online with us this Sunday on 16th of August in the evening at 6. So stay tuned for that. You will find the link on our YouTube channel for that talk. So make sure that you have a reminder for that and join in. Reut will be talking about herself, and that's going to be our first session about the course, which we will be starting after we finish the course with Ellen right now, which I'm sure you guys are enjoying so much. So I hope you had fun today, and thank you, Ellen, for joining, and we'll see you next Friday. Clear skies.
See ya. Bye.